Good afternoon. I would like to thank the organizers for giving me the opportunity to present to you today an overview of bioprinting. During the talk, I will describe the many types of bioprinting techniques that are available, as well as give you examples of how we're using bioprinting in our research projects. First, I'd like to describe just 3D printing. 3D printing is a form of additive manufacturing where a layer of material is deposited and then another layer is deposited and so forth in a layer by layer fashion to produce a 3D construct. Charles Hall is credited with inventing the 3D printer in 1984. However, he was not the only individual working on 3D printing at the time. There were a number of investigators in Japan and in Europe that were working on 3D printing, but he was the first to get his patent approved, and therefore he's credited with inventing the 3D printer. He used ultraviolet light to cure a photoreactive resin in a layer by layer process that formed a 3D structure, and he termed this stereolithography. This slide shows different types of 3D printing, all the way from polymerization, and that includes stereolithography, to material extrusion, powder bed fusion, a couple of types of jetting, direct energy deposition, and sheet lamination. This next slide shows those 7 major headings with a number of different sub-technologies under each heading. Therefore, you can see that there are a number of different technologies that one can choose depending on the specific type of application they want to 3D print. Now, moving on to bioprinting. 3D bioprinting is really a form of 3D printing, but it adds another layer of complexity because we attempt to build tissues and organs that uses cells and biocompatible materials. The 3D bioprinting allows the individual to really control the delivery of cells in a spatial orientation, as well as add other biological materials such as growth factors within the printed construct. And really, 3D bioprinting has the potential to overcome many of the current limitations that we face in tissue engineering. A little bit about the biomaterials we use in 3D printing. The first one listed here is hydrogels. And this is really a soft biomaterial that supports cell viability and function. And you can actually embed your cells within hydrogels prior to bioprinting, and then the biomaterial and cells can then be bioprinted to form your structure. They're both natural and synthetic hydrogels. The next one is curable polymers. And these are really to add structural support to your printed constructs. What you see here listed as polycaprolactone, or PCL, is really a commonly used polymer for bioprinting because of its relative low melting temperature, as well as its biocompatibility. These structural polymers can be used to print 3D scaffolds that then can be seeded with cells at a later time. This slide shows a list of hydrogels that are available for use in 3D bioprinting. As you can see, there are a number of natural materials such as collagen, hyaluronic acid, gelatin, as well as a synthetic pluronic hydrogel. This slide shows the structural biomaterials. And you can see PCL is listed there, as well as some other materials, polyurethanes. And again, these add a structure to your 3D construct. This slide shows different methods for bioprinting. Includes inkjet printing, extrusion printing, as well as laser-assisted printing. Laser-assisted really can be considered a jetting type printing, as we'll see a little bit later on. Now, to go in a little bit more detail about each of these bioprinting techniques, the thermal inkjet printing, as you can see here, it uses a thermal plate that heats up, and it causes a generation of a bubble that ejects small droplets of your bioink and bioink plus cells. And you can deposit these small droplets in a layer by layer fashion to produce a 3D construct. The next type of jetting based bioprinting is the piezoelectric printing. And that uses a piezoelectric actuator that vibrates at high frequencies that generates these small droplets of biomaterial that get extruded. And again, you can form a 3D structure in a layer by layer fashion. This again shows laser-induced forward transfer printing. And this is where you have an energy-absorbing layer. And then on the bottom of that layer is the bioink containing the cells. And then a laser pulse heats that energy-absorbing top layer that then causes the extrusion of a drop of your biomaterials down onto your substrate. And again, using layer by layer deposition, you can form a 3D structure. This slide shows you extrusion-based bioprinting. You can have pneumatic pressure deposition, where you use air pressure to push on your bioink, and you get a continuous filament of the biomaterials coming out of the nozzle. And again, you can use this in a layer by layer fashion and produce a 3D structure. Another way to extrude the bioink is through a piston-driven system, as well as a corkscrew delivery system that you see in the slide. Another form of printing is digital light processing. This is very similar to stereolithography because it uses polymerization. Just uses a different light source or a different apparatus to focus that light source. And here you have a 3D image generated on a computer that sends that information to a digital micromirror device chip that then processes that information and projects the images through optics down into your vat of biomaterials that are then polymerized in a layer by layer fashion to produce your 3D construct. Some advantages and disadvantages each of these types of bioprinting is given in the next few slides. And here you can see the advantages of jetting-based bioprinting is that it's fairly low cost. You can get high resolution using jetting-based bioprinting. And you also have options of multiple cell and material delivery for that bioprinting technology. But some of the disadvantages is that you're really limited on your biomaterial selectivity because you need to use low viscosity materials because you're pushing out small droplets of the biomaterial through a nozzle, and high viscosity materials just don't work in a jetting situation. There's some difficulty in scale up. The printed structures are weak because you need to use hydrogels, the low viscosity hydrogels. And because the structures are weak, there's really a limit in construct size. Digital light processing, its advantages is it's fairly high resolution and more rapid print speeds. But some of its disadvantages is that there's a limited availability of the biomaterials that you can use because it must be photocurable. And it really cannot be integrated with other types of biomaterials. And again, as with the jetting type of printing, the structures are weak. Extrusion-based bioprinting, some of the advantages is wide material selectivity, different types of cells, high cell concentrations, scalable. Some of the disadvantages is low resolution and the production of shear stress, which can decrease your cell viability, and print speeds can be a challenge. Investigators at WFIRM have developed an integrated tissue and organ printing system to help overcome some of the limitations that we see with the other types of printing technologies. With this printing technology, we can combine both hydrogel and structural biomaterial printing within the same construct. So we overcome many of the difficulties that we see with the other technologies. This slide shows a picture of the iTop system, and we can use many different cell types and biomaterials, as well as drugs, growth factors, can all be bioprinted using the iTop system. This slide just shows a schematic diagram of the printer, and you have an XYZ stage, as well as multiple print heads. They're all controlled by a computer. And here you can see you can print different cell types, as well as different biomaterials. This is a picture of the system you can see on the right-hand slide. Here is just a short video of printing ear structure. And you'll see that we are printing polycaprolactone as a structural component, and that's printing now. And then you'll see the second print head, which contains a sacrificial material. We need to use that as a support as we're printing a 3D structure. And then here you can see that we're using a hydrogel containing cells. So 3 different print heads, and all of these get incorporated into the construct. So the cells are present as the construct is being printed. And with this, you can see that we have a heated element over the PCL nozzle. That's to heat up the PCL to its melting temperature before it's deposited through the nozzle. And here you can see a completed ear construct, and around it you have the sacrificial material that can be washed away, and you're left with the printed ear construct with the cells embedded within them. This slide shows that you can have many different types of constructs with the PCL as an internal support, or as seen here, you can print 2 different cell types, one labeled red fluorescence, another labeled green. And you can see that the PCL is internal to the construct. The other construct you can see on the right side has the cells internal and external support of the PCL. You can print many different types of tissues and structures. You can see here a muscle, testes, liver, with multiple different cell types. One advantage is medical imaging. So you can use medical imaging to produce your 3D structure and you can then print an exact replica of that medical image. So you can take CT scans, MRIs, and use reverse engineering through a 3D CAD program, and then through a 3D CAM program to deposit this layer by layer and form a 3D construct from your medical image. And this just shows an example of that, where you can take your medical image, produce STL CAD and a motion program for the structural component, PCL, and then a cell latent hydrogel structure, combine those, and then print your 3D structure. And this shows that ear construct that was printed, and you can see once you remove the sacrificial material, you have that ear construct there. And then after maturation in vitro, you can see it lays down very nice collagen layer. And if you place these constructs in vivo after 2 months, it's very nice collage deposition within that, and the construct remains very pliable, and the cells are still viable. You can use this to print bone tissue as well. You can take a CT image of the a bony defect, and then print that exact structural dimensions and add your osteoblast into the construct, and then use that to repair a bone defect. We can also use print muscle constructs. And again, we're using a PCL pillar to add structure on each ends, and then fibers of hydrogel containing muscle cells, and they mature over time. These then can be implanted in vivo in a muscle defect, and you really get very nice innervation and vascularization within that bioprinted construct. You can print very complex tissues, such as a muscle-tendon construct. Here you use 2 different types of structural biomaterials, polyurethane and polycaprolactone, and 2 cell types, muscle cell, as well as a fibroblast for your tendon. And there's a 10% overlap in the structures there when you print. And here you can see that each cell, different cell type, is labeled with a different fluorescent marker. You can see the very nice junctional complex here. And then after in vitro maturation, it's a very nice junctional complex formed between your muscle and fibroblast or tendon printed construct. You can use this to print cardiac tissue as well. And here we can print both fibers, a web type construct, or a patch, and they all beat and function after printing. And then you can use these printed constructs to screen drug responses. Here you can see a control with the beat frequency. Add epinephrine and increases. If you wash the epinephrine out, it returns to normal. And if you add another drug, it causes an arrhythmia. You can see that. So they respond very nicely to different drug treatments. We also developed a skin bioprinter for burn injuries. And here you can see an early version of the bioprinter on the top right. And we can print layers of dermal fibroblasts as well as keratinocytes and place them directly in the wound. We've since produced a preclinical prototype skin bioprinter that you can see in the lower right. We have a laser scanner that we can scan the wound, take that information, and then print our cells directly into the wound. And this shows an animal model, wound model in a pig, and we printed autologous skin cells. And you can see here that the wound heals very nicely, and you have almost 90% reepithelialization at the second week after injury and bioprinting. whereas it takes up to 6 to 8 weeks to get that wound healed without bioprinting the cells. So in summary, I've given you just a very brief overview of bioprinting and described our integrated tissue and organ printing system and how we use that in our regenerative medicine and tissue engineering research projects. And it really gives us the opportunity to use this enabling technology to really leap forward in terms of regenerative medicine and tissue engineering. So I'd like to leave you with some of the limitations of bioprinting, though. We really need more biocompatible materials, both structural and bioinks. There's some problems with resolution that we need to address, as well as vascularization of larger printed constructs is a challenge, and a large number of investigators are working on that now. And also fabrication time. We really need to decrease the print time to be able to maintain cell viability from the very beginning to the end of the construct. And with that, I'd like to thank a large number of people that have worked in the bioprinting projects, as well as the funding agencies all the way from NIH to a number of foundations to the Department of Defense. And with that, I thank you for your attention. And I look forward to an opportunity to answer any of your questions at the end of the session during the panel discussion.